Right, let's get started. So I'm very pleased to introduce you to James Harrison, who's the data engineer at Flowminder, and today is going to talk to you about designing mobile phone data pipeline. Thank you. Over to you, James.
Great. Thanks very much, Sophie. Hello, everybody. So yes, let's get into this session. So today I'm going to be covering designing data pipelines for MPD for policy use cases. So the things we're going to cover are the types of input and output data that a data pipeline would be processing and producing. I'll go through some of the qualities that a good data pipeline should have, um, and talk through the different stages of data processing within that pipeline. And I'll also cover the considerations that will influence the design of that data pipeline. Things like the required compute resources, the layout where the processing takes place, and so on. So just to clarify things from the start, what do I mean when I talk about a data pipeline? This is a system that transforms, processes, and moves data from one or more sources to one or more destinations. So we have input data, which might be in a series of flat files, or might be coming from databases, could be coming from multiple different sources, different data types. Then a chain of processing steps that transforms that data into, firstly, intermediate data objects, and then finally some outputs that will then be in the form of, that might just be more data sets in a database somewhere, but also that could be compiled into maps, reports, dashboards, potentially a variety of different outputs for different purposes. So what are the learning objectives of this session? By the end of this, you should be able to identify internal and external stakeholders that are relevant for a particular MPD for policy initiative pipeline. Describe the types of outputs that that pipeline would produce, and where you would find the required input data that would feed into the pipeline. You should be able to explain why MPD data should be standardized for further processing, and describe some of the qualities that we would expect a good data pipeline to have, and also the considerations that will factor into the requirements of that data pipeline, and sort of within that, understand some of the factors that would determine the storage and processing infrastructure requirements for the data pipeline. So I'll start off by having a recap of the pre-reading material that I hope you will all have been able to have a look at in advance. I'll then move on to briefly covering navigating MNO data infrastructure, what data sets are there, where do they live within the MNO, who's responsible for those. I'll then talk about the qualities that a good data pipeline should have, and then that will lead on to some best practice for developing a data pipeline, and I'll be using a case study example to talk through that bit, and then I'll summarize what we've covered at the end. So firstly, a recap of the pre-reading material. So aligning and managing stakeholders. We can separate the stakeholders that are relevant for a data pipeline initiative into three categories. So we have the providers first. So these are the owners and controllers of input data sets. So this might be staff within an MNO who control the MPD data feeding into this, the cell locations, things like that, or potentially within a National Statistics Institute. So maybe additional data sets like population reference data, maybe survey microdata that needs to be linked in, things like that. And these stakeholders will be the source of information about the input data sets. So where are those data sets stored? How big are they? What quality assurance do we have of the completeness and quality of the data within those data sets? And what structure is that data in, so that we can figure out how to integrate that into the pipeline. We then have the next category of stakeholders, which are the maintainers. So these are the people who are responsible for building and maintaining the pipeline. Um, if you're in this session, um, this may well be you that would fall into this category in a particular data pipeline initiative that you're involved in. But important to note that as well as just those directly responsible for implementing the pipeline and keeping it running, this could also include staff that are in indirect supporting roles. So this is, for example, whoever is responsible for maintaining the hardware infrastructure that a pipeline is running on. Also, some of those provider stakeholders I mentioned at the start. So the people providing the data sets, if those data sets are not already routinely made available for similar purposes, there might be extra work on them to make that data available, keep the data flowing into the pipeline in the first place. So then they might also become maintainers. And all of the maintainer stakeholders will need to be aligned on the aims of the pipeline and the roles that they will take within the building and maintenance of the pipeline. And then the final category are the consumers. So these are the users of the outputs from the data pipeline. So this could be direct users, the people directly accessing the data sets, reading the output reports, things like that. But also indirect users further down that chain. So policymakers that are taking informed advice from experts looking at the outputs of the data set, and also the affected population. So the people that this data relates to, the people who will be impacted by the particular use case in question. Obviously, they are also a stakeholder here. Their needs and their considerations will factor into the design of the pipeline. And so essentially this category of stakeholders are the ones that will determine all aspects of the outputs, the content of the data outputs, the format in which that is produced. So that could be just raw data sets, or maybe it's reports or interactive dashboards, and also the timing and frequency of those outputs. So for example, if the outputs of the data pipeline are needed as input into a monthly alignment meeting, then that would affect the timing of when those outputs need to be ready. And then, of course, that pushes all the way back through the pipeline. So the requirements on those outputs will then affect the requirements of all of the intermediate processing steps and so on. So what types of outputs might our data pipelines have? So firstly, there might be outputs that are not, the final visible outputs, intermediate data sets that are calculated as part of the overall calculation. So these are not things that are directly disseminated out to end users, but they are produced along the way within the pipeline, maybe just stored temporarily, maybe kept longer term so they can be used for other use cases later. And then we have the indicators. So these are the actual main data outputs from the pipeline to serve the use case. And there might also be diagnostic outputs, so other data outputs that are not directly the outputs that are needed, but are separate outputs that give you an idea of the quality, any possible issues that could affect the way that those indicators should be interpreted. And maybe we're not just producing data sets. It might be that particular stakeholders will not be in a position to directly interact with data in a database, for example. So we might be compiling those outputs into maps and visualizations to better represent what's shown in the data. Those in turn could be included into reports, maybe with a written summary interpreting the data outputs, or similarly, maybe into an interactive dashboard. So this is going to be quite similar to a report, but more interactive. Users can go in, interact with the data, select date ranges, areas of interest, compare different data sets, and so on. And as I said, the format, the frequency, and the method of dissemination of these outputs is going to be very dependent on the use case, on the needs of the users, and this will strongly influence all of the pipeline design. I'll now briefly cover navigating M&O data infrastructure. So where are the source data we need for an MPD initiative? Before building the pipeline, we need to work out where that data is coming from. And this might require combining data managed by various different teams within a mobile network operator, potentially even stored in different databases. So this could be, for example, the CDR data was most likely managed by the billing team because it's produced for billing purposes. Might also be accessed by the business intelligence team and used internally within the M&O for other purposes. There might be other positioning data that's similar in structure to the CDR. So yeah, still location points in the for each active device, but might be recorded for different purposes. For example, signaling data. Maybe the network operations team is recording this data to maintain the effective and efficient operating of the network. There might be other teams involved here as well. The other half of the equation that we'll need is the cell positioning and coverage data, so that we can actually link active cell IDs appearing in the MPD data to the locations of those. Typically, this would be the radio networks team is responsible for these, and they may well be stored separately, updated separately from the CDR data. So there are potentially different teams that need to be aligned on this. And then the other category of data that the MNO might be providing that would be needed for this pipeline, potentially client portfolio data. So this could be things like the handset type that the subscriber is using, customer segmentation metrics, other metrics that the MNO collects and stores about the subscribers. Different use cases will need different things. This may or may not be relevant for a particular use case. But this again might be managed by a different team, maybe the commercial team. Again, business intelligence might well be accessing data sets like this. So it will depend, it will vary a lot from one MNO to another as to how this is structured, but there are potentially a lot of different teams with a lot of different data sets that need to be aligned here. And for each of those data sets, we need to identify where are they? What database does the data set live in? And how do we access that data? How do we get it into the pipeline? Who is responsible for each of those data sets? So which team, and ideally within that team, who's the point of contact that we can speak to find out the relevant information that we need to identify all the information we need to integrate the data as an input to our data pipeline. What quality checks are applied and monitored? So can we be sure that there's no missing data, no time ranges that have got lost somewhere? Are there checks to ensure that for example, the device IDs, the cell IDs appearing in this data set are valid? It's possible there are invalid values there. So yeah, we want to know what checks are already being applied, how confident can we be in the quality of this data? Because that would determine how much we need to check these things ourselves within the pipeline. How frequently and how quickly is each data set updated is another key consideration. So would we be able to access new data daily? Is that coming in continuously in a streaming fashion? And how long does it take for new data to be available? So if somebody makes a phone call yesterday, will that appear in the CDR data accessible today? What's the lag there? How quickly can we get that data? And different data sets will be different. Maybe the cell information is updated less frequently, and it might take longer for a new cell tower to appear in the data set there, because this is a slower moving thing. And how do we combine the data sets? So what fields in a table of CDR data would be used to join those events to cell locations in another table, maybe in another database? How do we link all of these things up? So those are kind of the considerations for the input data set coming from an MNO. I'm now going to cover some qualities that a good data pipeline should have. So these qualities I'm going to go through are data standardization, so getting the input data and then all of the intermediate data sets and the output data into a standard format that is well understood, documented, that can be built on easily. Quality assurance, so checking the quality of the incoming data, making sure that there are no issues. If there are any issues, catching those and dealing with them appropriately. Recurrent and reproducible processing, so making sure that data processing happens in a recurrent manner, preferably as automatically as possible to reduce manual effort and reduce the possibilities of human error, and in a reproducible manner so that we can go back and rerun calculations later if data changes, if the method changes, without needing to worry about working out what else might have changed along the way. Maintainability, so we want to make sure that our data pipeline is designed and built so that it can easily be maintained, kept running without too much additional effort, and can be updated easily as well. Performance and efficiency, making sure that the data pipeline operates efficiently, data outputs can be produced in a timely manner as needed, without significantly impacting on other processes running in parallel. And then the final point, security and data governance, keeping the sensitive data in this pipeline safe. So starting with data standardization. What do I mean by data standardization? This is getting data into a consistent structure and format. So tables with clear column names, data types that are appropriate. So for example, using integer data types if the data in those columns are integers, well understood text value formats. So for example, date strings should be in a clearly defined format, so we don't have a mix of different formats of dates. Things like using unique IDs for locations to avoid problems with spellings, different ambiguous names for locations, things like that. The structure and format of the data should be clearly documented for convenient reference so that anyone working with the data can look up what's there, what do these columns mean, what structure can we expect in the data. And this applies to all stages of the pipeline. So this, I'm not talking about just transforming the input data into a standard format. This is also making sure the outputs are in a standardized format, so that those can be well understood, and also all of the intermediate stages of the pipeline. It may be that a particular intermediate table is used for one purpose now, but later we might want to add a different use case in that also needs to use that. So we need standardized intermediate data as well so that we can build on any stage of the pipeline. Where possible, we should enforce requirements on the data using constraints in a database. So for example, if there's a column that must not have missing values, we could put a not null constraint on that. If there are uniqueness requirements, for example, only one location per device per day in a particular table, we put a unique constraint on that table to make sure we don't get duplicates. Foreign key constraints. So for example, If we have one table of device locations with cell IDs, we want to make sure that each of those IDs corresponds to a known cell in a separate table corresponding to the cell locations. And by putting these constraints into the database, that means it's impossible to insert data that won't be valid. So if there are any issues, they'll get caught early and won't pollute possible outputs in a way that may not immediately be visible. Another consideration is, where relevant, if there are particular accepted standards more widely for the structure of a particular output. And this is often the case if we're working with national statistics, for example, there might be accepted standards for how a particular type of output should look. We need to make sure that the outputs of our data pipeline are in a structure and format that is aligned with those standards so that they can be easily picked up and built on with other existing tools by other people that are not maybe familiar with the internal workings of the pipeline. Why is this important? Accuracy is a key one. It's a lot easier to catch any data quality issues and prevent them from occurring if the data structure is easily understood, so we can easily compare data to a reference and make sure that it looks as it's expected to look. Maintainability is another key one. We can update and extend the pipeline more easily if we have clear documentation and a clear understanding of what the data will look like at each stage within the pipeline. Comparability with other data sets and interoperability with other systems. Those will require standardized data so that one side can be updated and adjusted without needing to know any subtle internal details of the other side, because the data is standardized and the structure is well understood. And data governance is the other key thing. It's a lot easier to maintain audit trails and implement any data governance policies if the structure, the location of the data, and so on is well documented, well understood. Next quality I'm going to talk about for a good data pipeline is quality assurance. Data issues will happen. No data set is perfect. We need to prepare that some things will go wrong with the data. There might be missing data. There might be invalid entries. We want to catch those early using QA checks so that they don't propagate through the later stages of the pipeline and take appropriate action. We can roughly split the types of checks we would be carrying out into two categories. So syntactic checks that are checking the structure of the data is correct. So this would be, for example, catching corrupted files, null data in fields that should not have missing data, duplicates, and then semantic checks that check the data content is interpretable, that it makes sense. So checking the meaning of the data rather than the structure. So for example, impossibly fast movements that might be syntactically valid, but we see a particular device has jumped 1,000 kilometers in 5 minutes. It's not possible. Something's clearly wrong there. And other examples of that. I won't go into too much details of these because more details of the types of QA checks that we might be carrying out will be covered in session 2.3.4 later. So how do we implement quality assurance checks in our pipeline? Along with actually carrying out the checks on the data, we want to record quality metrics. So for example, counting the number of rows affected by data issues, recording maybe the average or the maximum value of a particular field, things like that. Why do we want to do that? It's because it helps with routine monitoring of system health. So it might be that there's not a particularly anomalous value standing out that we can alert on, but by looking at these metrics over time, we can see more gradual changes that might hint at something maybe not being quite right. Some checks we want to perform might require comparing to previous values. So if we want to detect, for example, a number of CDR events per day that is well outside the normal range we'd expect, we need to know what that normal range is. So if we've recorded that on previous days, then we can more easily compare and detect anomalous values. Manual checks and debugging, if we detect problems, will benefit from having these quality metrics. So maybe we have an automated check that flags up something's gone wrong, but then we need to go in manually and work out what went wrong. So by looking at these quality metrics, we can figure out what's happened there. And then the final point here is that later processing steps in the pipeline might use these quality metrics. So for example, if there are particular devices that have a very small number of events on a particular day, we maybe don't need to take action early and stop aspects of the pipeline for that. But later stages of the pipeline might need to filter out these devices because a particular location inference method, for example, might not be reliable in that case. So we can change what happens in terms of the later processing using these quality metrics. And then the other aspect of this is if we do detect quality issues, these should trigger some actions. So that might be data cleaning. Maybe we just drop the invalid data and move on, just throw it away. We probably want to alert relevant staff members. So if there are issues, rather than just blindly moving on and not telling anybody, we want to alert relevant staff members so they can go in and see what's gone wrong, particularly if it's a large data issue. Maybe if it's a few invalid rows of data, we drop those, we move on. But if there's a large amount missing, someone needs to go and see what's going on and maybe fix that. And as I said on the previous slide, this could influence later processing stages. So maybe skipping, we might want to skip some of the outputs, but not all of them if we don't have enough data for a particular output. Or maybe we still produce all of the outputs, but we need to produce a data quality advisory along with that so that end users can see there might be other issues at play here that might affect the way the outputs should be interpreted. And to go along with that, we might be producing diagnostic outputs. This could be data sets or reports to go along with the main indicators to advise on any data issues that could be affecting those. And QA checks should be automated if at all possible, even if the relevant aspect of the pipeline is not automated. So maybe this is at the stage of ingesting an ad hoc data set that is not updated at regular intervals. It requires someone to go and manually ingest this new data set. Ideally, those QA checks should be built into whatever script is used there so that we can't have a situation where somebody ingests the data but forgets to run the QA checks. That should always happen. Next quality I want to talk about of a good data pipeline is data standardization. No, sorry, recurrent and reproducible processing. So the point here is we want to minimize the manual effort required to keep the pipeline running and ensure that outputs can be reproduced at a later stage if we need to. So to do this, we want to be processing data with reusable scripts. So for example, written in Python or Bash, scripts that can be reused maybe with different parameters each time to avoid having to do too much manual work each time. And going beyond that, if we've got data in parameterized script, we've got processing steps, sorry, in parameterized scripts, we should be able to automate those for recurring tasks that happen at repeated intervals, we can automate. So for example, on Linux systems, cron is a simple time-based scheduling tool that can be used to run a task regularly at defined intervals. Or for more complex workflow orchestration, Apache Airflow is a useful tool for this. So again, time-based scheduling, but you can have a series of tasks that each depend on each other, and also we can handle event-based scheduling, for example, running a task when data becomes available rather than purely by time. So yeah, I'd encourage you, if you're looking at automating things, have a look at Apache Airflow. It's a useful tool. Fault tolerance is a key thing here. So we want graceful error handling if something goes wrong. Sometimes a task may fail, maybe just because the connection to a database temporarily goes offline. So if that happens, we don't want to just crash and shut down the entire pipeline and require someone to come in and rebuild it all. We want to handle that error gracefully, ideally retry a few times. So if it's just a temporary issue, then we keep retrying until that data transfer works. Monitoring is a key thing here. So we should be logging everything that's going on within the system, all of the operations that take place, keep a log of those so that we can go back later and see what's happened when. And alerting, so if a particular task fails, send an alert so that someone's aware of that, someone can go and address that. And final point here, data lineage and version control. So this is coming to the reproducible aspect here. We need to make sure that we know not just that the pipeline is working and operating, but what has been produced and how is it produced. So data lineage, keeping track of what data sets have fed into each new data set along the chain, what data was used, so that we can go back and check, if there's a problem with one of the input data sets, what outputs will that have affected? What do we need to go back and rerun? And version control of all of the code used in the pipeline, so that if we change the method for calculating a particular output, we have a record of how that used to be calculated and how it's calculated now, so that if we need to go back and check and reproduce a particular previous output, we can go back and find out what code was used, what method was used, and from the data lineage, what data were used to produce that output. Next point, maintainability. So we need to have clear, well-documented and version-controlled code to implement our pipeline. We need to know what is the pipeline doing, where's the code that is defining what it's doing, make sure that's well documented so that can be picked up by somebody else coming in maintaining the pipeline, or even if you built the pipeline yourself, that you have a reference to look back to if something's not quite working, or if you need to go back and check how something is implemented. Ideally, we want to design our pipeline in a modular way. So build the whole pipeline up from small independent tasks that we can debug and update separately. And we can easily build on top of those with new modules to extend the functionality. This means that if we need to debug a particular part of the task, or we need to make an update, we don't need to worry too much about potentially a whole web of interconnected dependencies within the pipeline. Each component is reasonably well isolated from the rest of the pipeline, so we can update those more simply. Really, we should be testing all components of the pipeline before we deploy, and making sure that a particular function is doing what it's supposed to do before we put it into production, so that if there are any problems, we catch those before impacting any real outputs. And we want to make sure that we can update the pipeline in a streamlined manner with minimal disruption. We don't want to have to take the whole pipeline offline for a few days while we do a big upgrade or something like that. We want to minimize the time it's going to take to swap out or update components of the pipeline without losing the, the timely production of outputs as a result. And this can be achieved through the modular design I've already talked about. Being able to update just one component at a time can be very helpful. Well-documented version-controlled code and the testing, all of these factors feed into making it just easier to update the pipeline efficiently. And this can be greatly helped by establishing an update process. So this might be code review of any changes to the code that are made, followed by testing before those changes are deployed. A process, a well-defined, clear process that someone can follow to deploy those changes and also to roll back any changes if those are deployed and then we find something wasn't quite right. We want an easy process to roll back to things to how they were while we fix and then work on redeployment of that new feature. And it's important to define clear roles and responsibilities for this process. So who is responsible for each of these steps, so that is streamlined. We don't run into any unexpected issues halfway through a deployment process that then might halt things for an amount of time while we fix that problem. It's something we want to avoid. Performance and efficiency is the next quality I want to talk about here. So clearly we want our pipeline to run efficiently and produce outputs efficiently. Considerations for this, we want to make sure that data processing completes in a timely manner. What that means, a timely manner, will depend on the use case. But for example, if this is for a crisis response use case, for example, it might be very important that we get outputs as quickly as we can after an event occurs. Or just in a more routine situation, we certainly don't want to be in a situation where, for example, it takes more than a day to process each day of data coming in, because then we're never going to be able to keep up with the processing requirements. So we need to make sure that everything operates efficiently there. We need to ensure that we've got sufficient storage, and potentially, if this is a pipeline that's going to be operating for a long time, maybe it's running for several years, we might need a lot of storage to keep a long time series of data. And we need to also factor in here data backup. Ideally, we really need a backup of the critical data for the pipeline so that if we lose that main copy, we can recover that. We want it to be able to handle growing data volumes over time. This is particularly a thing with MPD data. Maybe if there's more and more uptake of using mobile data over time, then the volumes of data that we're seeing in CDR data sets might be growing significantly over time. The size of the subscriber base might also be growing as well. So if this data pipeline is going to be running for a while, maybe in a few years' time, the data that we're processing on a daily basis is going to be a lot bigger than the data we're processing on a daily basis now. So we need to be able to handle that. And that might be a case of planning ahead with over-spec hardware. So might we need a more powerful server than we actually need at this moment in time, so that it's going to be able to keep up in future. And or maybe we push that down the line and we say we're going to have scalable compute resource so that as the data volume grows, we can add more compute resource to the system. And in this case, we need to make sure that our system is designed so that we can scale in that way without needing significant fundamental redesigns of the architecture along the way. And then the other side of the equation here, optimization. We want to make sure that the operations of the pipeline, excuse me, are efficient so that we minimize any unnecessary hardware costs for processing power and storage. So not keeping around any more data than we need to, ensuring that any processing steps can operate efficiently, make good use of parallelization, things like that. And the final point for qualities of a good data pipeline, security and data governance. So the various security considerations we'd want to take into account for a data pipeline. Access control is a key one. We're dealing with sensitive data here, MPD data, sensitive personal data. We need to make sure that only the necessary people have access to the data. So this means restricting access to the system to only those who really need it. And we need to keep a record of what access permissions are required so that we can audit that, make sure over time we keep track of who's got access to what. Server hardening and data encryption. So making sure that nobody can gain access to the system when they haven't been given access, resisting attempts to hack into the system and so on. And yeah, data encryption, keeping data encrypted as much as possible. That might not be necessary at all stages of the pipeline. It is a trade-off. But yeah, ideally where possible, sensitive data we want to be keeping encrypted, so that even if somebody does get access to that data when they're not supposed to, it's encrypted so they can't do anything with it. And then the final thing, keeping audit trails, it's really key here. So you need to keep a record of everything going on in the system, who is doing what, so that if there is an incident, a data breach, something like that, we can catch that, and we can properly investigate what went wrong. There are various compliance measures that might feed into the design considerations for our pipeline. For example, data localization, there might be regulations that mean that the MPD data needs to stay within the country or even the actual premises of the data owner. Need incident response procedures, so we have a clear process if something goes wrong in the data pipeline. Labeling of the sensitivity of data sets. So how some data sets will be very sensitive, containing a lot of personal data. Other data sets maybe not so sensitive. So we need that labeling so we know which data is most sensitive. Data lineage, I've already mentioned previously with regard to the reproducibility of outputs, but also it's key here for data governance purposes. For example, if an individual objects to the processing of their data, we need to be able to work out which data sets in the system contain data from that individual. So the data lineage is key there for keeping track of that. We might have policies for how long a data set needs to be retained after it's finished being used, and when it needs to be deleted. And then privacy protection. So ensuring that any outputs protect the privacy of the individuals whose data is being processed. And I'm going to cover these points in more detail in the session next week, 2.3.3 on privacy by design. I'll move on now to best practice for developing a pipeline. And for this section, I'm going to be using the Eurostat multi-MNO pipeline as an example here. Don't worry too much about this large, complicated diagram. I'm going to zoom in on the relevant bits and talk through the important points. Also, we don't need to worry too much here about the specific use case that this pipeline is serving. I'm using it more as a reference to show the stages and the structure of a data pipeline. And for that, I think it's a good example. This is a pipeline that produces indicators at various different timescales, daily, monthly, yearly. The use case here is for official statistics within the European Union. It's been co-developed by a consortium of organizations, so this is not just built by one organization, and it has been tested in several European countries on real M&O data. So I think for those reasons, this is a useful case study to use as an example here. So what are the stages in this data pipeline? First stage, data ingestion. It's getting the data from the sources, various sources, into the data pipeline and cleaning it up. There's then the data processing and the production of outputs. So various stages of processing feeding through eventually to the output indicators. And the final stage, which is actually out of scope for this particular example, is then the dissemination. So once the data have been produced, where do they go to? Who do they go to? How do they get there? And in what format? And then throughout the pipeline, this is not a separate stage, but throughout every stage of the pipeline, QA checks and alerting to detect any issues along the way. So firstly, data ingestion. This is the stage that we often call ETL or ELT, for standing for extract, transform, load, or sometimes extract, load, transform, depending on the way that things are structured. So this is the process of getting data from whatever source that's coming from into our system. Standardization of input data will happen at this stage. So we're taking data from potentially several disparate sources, different systems, different providers in different formats, and we're combining those into a known structure, a standardized format that the later processing stages of our pipeline can operate on. We need to ensure integrity of the data at this point, so catch any problems in the source data early before they can propagate through the pipeline. So if we've got syntactically invalid data that just doesn't fit the data structure that we need to either remove that, just throw it away, or raise an error so that we can manually intervene, work out what's gone wrong, and fix the issues. The frequency of ingestion can be influenced by the frequency of the data source, and is not necessarily the same as frequency of the production of outputs. So it may be that we're ingesting CDR data, for example, on a daily basis, even if the outputs are only produced once a month, maybe. And the different data sets might be updated at different frequencies. So for example, it may be the case that cell coverage information is updated less frequently than the CDR data. This might be happening at different points in the system. If the system is split across different, if the pipeline is split across different systems operated by different teams, different organizations, then different data sets might be ingested at different stages into that, maybe into several different databases. So the Eurostat example, I'll go through the data ingestion stages of this. So at the top here, we have the ingestion of the network topology data. So this is either coverage maps or the parameters of network cells that can be used to estimate the coverage maps. These will be extracted from the source within the MNO, cleaned into a standardized structure, and then those are transformed into a spatial propagation model for each cell. And in the case of this Eurostat example, that ideally happens on a daily basis. The next box down, we've got the ingestion of the MNO event data. So, for example, CDR data or signaling data. Again, extracting this, cleaning and transforming it. And in this case, this is transformed into an ordered time series of events per device per day. And again, ideally, this is happening at daily frequency. And then there are other auxiliary data sets. So for example, geographical data, maybe administrative boundaries, calendar data, so the details of which days are public holidays, things like that. These might be updated less frequently, maybe on a just an as needed basis rather than at regular frequency. I might be interested at different stages. So for example, if we've got population reference data for bias adjustment, that's maybe only needed at the final stage of processing. So might be ingested at a different stage. Next stage of the pipeline is data processing and production of outputs. So this is a chain of processing steps where each step takes one or more data objects as inputs and creates or updates other data objects as outputs. So the first steps in the chain will be operating on the clean source data that's just been produced by the ingestion stage I've just covered. The final steps in this chain will be producing the outputs. So this will be the indicators, any diagnostic data sets that are produced along with those, and or visualizations, reports, and summaries incorporating those indicators. And then there could be any number of steps in between producing intermediate data objects that may be just temporarily produced and then thrown away, or maybe those are produced and stored for use in other purposes later. And in terms of what those processing steps might look like, this is going to be covered in section 2.4, where we'll go into more detail of the methods that might be used for this. So coming back to our example of the Eurostat multi-MNO pipeline here, the data processing steps here are I've split it into multiple processing stages here. So the top box here is the transformation of cell coverage information to location probabilities. So I won't go into the details of the methodology here, but this is essentially going from a map saying which areas are covered by this cell to instead a map of if a device connects to this cell, where are they most likely to be? That then feeds into the per device analysis along with the cleaned event data. So this starts by producing data as a daily summary, so a stay location for each device each day. Those then feed along the chain into a midterm processing module, so producing, for example, monthly estimated home locations. And then those in turn feed into a long-term processing module that produces yearly estimated home locations, for example. And then the final stage, the final box at the bottom here, is the aggregation and calculation of indicators. So this is going from these individual device level summaries, filtering out any devices that maybe are not ordinary individual phone users, aggregating those, so going from having a single location per device to a count of the number of devices in each administrative region, for example. And then the calculation of indicators from those, which might involve modeling combination with other population reference data sets to adjust for biases in the data. This whole pipeline is designed with a modular design. This is one of the key qualities I mentioned earlier of a good data pipeline. Each of these blue boxes shown is an independent function that can be swapped out, updated, or replaced in future. And new boxes can be joined in with new functions to support different use cases if there are different use cases that want to be covered by this pipeline in future. One key design consideration in this particular pipeline is that each function can access all of the data objects produced by previous functions. So the data objects being um, the cylinder shapes in this diagram. So each function can access all of those from any earlier stage in the pipeline. But later functions can't update earlier data objects. So there's a directed flow of information. The information flows from the start of the pipeline through to the end. We don't get stuck in feedback loops. And then the final stage of the data pipeline is this dissemination stage. This will depend very heavily on the use case and the end users of the pipeline. For example, we might be just calculating these output indicators and then pushing those into a repository. That might be a private repository, a database belonging to the organization that's going to be using the data, or it could be a public repository maybe that can be more widely accessed. Or maybe we're updating an interactive dashboard that will allow users to interact with the data, combine with other data sets, explore data in different areas, and so on. Or maybe we're compiling into PDF reports that will then be sent out by email to all of the users that are interested in those. And there are several factors that can influence the type of outputs, the format of those, and the frequency of those outputs. For example, the purpose for which outputs are used. So, for example, the frequency of outputs will be determined by what they'll be used for. Is this a high resolution, looking at, for example, individual presence in different locations on a hourly, daily basis, or is this looking at longer term population changes over time, in which case the frequency of outputs might be lower. The technical or data literacy of end users is another key consideration here. So if, for example, the end user is staff at a National Statistics Institute, they will be pretty familiar with working with data, so giving them raw data sets is going to be okay. Although that comes with the caveat they may not be familiar with working with MPD data. So the biases and limitations of the data set might still need to be spelled out and documented either through maybe a README along with the data, or some training of those end users to make sure that they understand the outputs being produced. Whereas maybe users don't have the same level of data literacy, they're not going to be comfortable with just picking up a data set and using it. So in that case, perhaps a report with some pre-produced visualizations and some manually written summaries, perhaps summarizing the interpretation of the data, would be more helpful. Another consideration is the environment in which these outputs will be accessed. For example, we could imagine if these outputs are to be used by survey teams out in the field, potentially in areas with limited or no internet access, an online dashboard is probably not going to be so useful for that. So maybe there would be it would be more useful to have printable reports that can be taken out into the field and used. There are lots of factors across all types of all considerations of these outputs, depending on how they will be used. And as I said earlier, I've been working through with the Eurostat pipeline as an example, but actually this point is largely out of scope for that. In that case, the pipeline is producing indicators in a database for use by a National Statistics Institute, but actually they would be the ones operating that last stage of the pipeline. So there's no need to convey that information further within the scope of the pipeline. And then QA and alerting is a key point that's not a separate stage of the pipeline. These steps should be integrated throughout the pipeline. At every stage, we want quality checks to make sure that the data look as they're supposed to look, and we can catch any errors that occur. Check the validity and the reliability of the data, and to produce diagnostic metrics so that those can be monitored and reviewed. So this is covering the points I talked about earlier. We need to record those metrics, take appropriate action according to what's discovered with these QA checks, and alert the responsible people if there are issues detected, for example, by automatically sending an email with a summary of the problem to a data engineer that can then go in and have a look. Another point to highlight here is that this may involve manual review stages. We may want a step where there's a human in the loop. For example, at the output stage, before that final report gets released to end users, maybe we want a manual step where a human expert comes in and has a look at that, makes sure that there's nothing weird looking in the data that we haven't caught along the way. And if there is, they can add some interpretation to that, decide what that means, what end users should take away, so we're not putting out misleading data. And as I said earlier, more details of the specifics of QA checks that we might want to be implementing here will be covered in session 2.3.4 later. So in the Eurostat example, I can point you to where the QA checks are happening. So at the stage of ingesting the network topology data and the event data, there are syntactic checks happening at this stage. So checking that the data coming in has the expected structure and is valid. At that stage, we purge the malformed data. So any data that doesn't fit the required structure, we throw away at this stage. Produce those quality metrics that keep a record of any information about issues. And then launch warnings, send alerts if any issues are detected so that someone can come and have a look. Also, in the case of the event data, we're calculating device activity metrics. So this can be things like the number of events that a device had in a particular hour. And we can use these later, for example, to filter out devices that have too few events. So for example, if a particular device is insufficiently active to infer a location, then we might want to filter out those. Similarly, if a device has a very large number of events, maybe they're not an ordinary phone user, that could be a call center or something like that. So again, we might want to filter out those. And again, as with the other stages, if we detect issues, launch warnings so that somebody can have a look at those. Then once we get into the processing stage, there are semantic checks at the device level, so combining the event data with the network topology data so that we can see things like if there are impossibly fast movements in the data, things like that, or cell IDs that look valid but actually don't correspond to any known cells. We can remove any events that don't make sense so that they don't pollute the mobility outputs that we produce later. And then finally, quality checks on the output indicators. So in this case, this pipeline is for official statistics purposes. There are a lot of quality indicators well defined for official statistics purposes. So these quality checks on the outputs will be conducted in line with those. So where should the tech processing take place in our pipeline? We've gone through the stages of the pipeline, but where do these actually happen? It doesn't necessarily need to all happen on a single system. This could be split between multiple environments. It might be on-premises hardware, as well as some steps happening in the cloud. This could be separated between the systems of the data owner and a technical service provider. And there are a lot of factors that could influence this. So as I briefly mentioned earlier, there might be regulations that affect the what we're allowed to do in terms of data localization. Maybe the personal data or commercially sensitive data as well might need to remain within the premises of the MNO, so that couldn't be taken out and processed on a different system. Whereas once the data's been anonymized and aggregated and is less sensitive, maybe that can be shared more freely, could be processed in different locations. Integration with other existing systems and data sets is another key thing. So for example, adjusting for biases in the data might be using reference data that belongs to a National Statistics Institute. Maybe that data, that reference data, needs to be handled within their systems. So at that bias adjustment stage, the data would need to have been taken out from the MNO and processed within the systems of the NSI. Data size is a key one here. The MPD data sets we're dealing with here are typically quite large, with data from millions of individuals over potentially long time spans. This might require larger compute resources compared to aggregated data later on, which are typically much smaller data sets. They could be handled on smaller, cheaper hardware elsewhere, giving more flexibility. And linked with that, what's the available hardware already? Typically, we would expect the MNO providing the data will already have infrastructure capable of processing these kind of large MPD data sets because they're already doing that for business purposes. So it may well make sense to integrate those early processing steps within the hardware that already exists within the MNO. The other consideration I want to cover here is the intellectual ownership. So I don't specifically mean necessarily legal ownership here, but the methodology used within the pipeline might be developed by different organizations. Perhaps a technical service provider is specifying and developing the methods and models, and they would want control of how those are implemented. So the processing stages there using these methods would want to be on a system where that technical service provider has control. So they're not kind of doing that blind and relying on somebody else who maybe doesn't have the same understanding of the methods to do that implementation correctly. So in the Eurostat example here, this is a pipeline that combines data from multiple different MNOs and actually allows for two possible scenarios for how the pipeline is divided up between systems. So in the basic approach, all of the individual level data is processed up to the point of aggregation and anonymization within the premises of each separate MNO. And then those outputs are then transferred to the premises of the NSI, who then handles the bias adjustment and modeling stages. Or alternatively, an advanced approach where the early stages of the raw MPD data processing happens within the MNO parameters where the hardware already exists. But then the individual level daily summaries are transferred out from each of the separate MNOs into a single secure enclave, so a cloud environment where no individual one of these MNOs has access, but the data can be processed together in a secure way and aggregated together, and then those aggregated outputs are then transferred to the NSI for adjustment and modeling. And yes, so there's two situations there in this example, but there are commonalities between these two. So in both cases, the full raw MPD data, the very large data, is processed within the MNO where there's already infrastructure existing, already existing components of the pipeline, most likely, that can be used from what the MNO is already doing for business purposes. This follows the principle of data minimization. So only the necessary data are ever transferred out of the data owner's premises, whenever taking data anywhere where it's not needed, to keep that data as safe as possible. And in both cases, the final modeling and estimation is handled within the NSI. They're the ones that are specifying the methods and have the necessary auxiliary data sets for the bias adjustment and modeling stages. Now, I will quickly cover some of the challenges that come from dealing with large data. There are various aspects of this. First one, data processing capability. So this is parallelization, how many compute cores are available, how much memory is available, what's the speed at which data can be read and written from disk. All of these affect how quickly outputs can be produced. There's then storage capacity, which is going to impact how long the data can be retained. And this is retained for everything from archiving of data computed, keeping the data available to be able to recalculate outputs later if we have a change to the method, and also regulatory compliance. We may have requirements legally or from various policies on how long data needs to be retained after we finish using it. So we might need to make sure there's sufficient storage capacity to keep hold of that. Network bandwidth and latency is a key one for both dissemination of outputs, but also, and perhaps more importantly, internal data transfer within the pipeline. So if data sets are being transferred between different systems within the pipeline, we need to make sure that can be done efficiently, and that will be limited by the network bandwidth available. And when it comes to optimizing data pipeline to improve performance, the key thing is to start by identifying the bottlenecks. Is it the CPU processing power? Is it the memory? Is it disk read and write that are limiting the speed of the processing? How long is spent in each of the processing stages? It's very important to do this profiling. Don't just go out and guess which bit you think is the slowest, because you may well find you spend ages optimizing one small part of the calculation, which actually it turns out is insignificant in the overall picture. So that's brought me to the end. I'll quickly summarize. So I started off by saying that M&O data needed for input to a data pipeline might come from multiple teams, multiple sources within the M&O. And it's important to scope out who has access to what data. Good data pipelines should be automated to reduce manual effort, maintainable to reduce manual effort in keeping the data pipeline running. They should run efficiently, and they should be secure to keep the sensitive data within them safe. And throughout the pipelines, we should be integrating QA checks, extensive monitoring and logging of what's going on, and alerting so that we know if something does go wrong. And a lot of these are factoring into the data security side of things, which I'll be covering in my session next week. And pipeline design is influenced heavily by end user requirements, but also by the size of the data and the available hardware for processing that data, and also the details of who owns the data sets, who owns the methods for processing those data sets, and any applicable regulations that determine where and how data are allowed to be processed. Thank you. I'll finish off by just giving you some links to further reading. These links should all be in the OLC, so don't worry about copying them down from here. But I want to point you to the details of the Eurostat multi-MNO project I've been using as an example. Particularly, I've got a link here to the methodological framework for that reference pipeline. Also, a similar example from a slightly different angle, FlowKit, which is the MPD analysis platform that we've built and we use here at FlowMinder that I work on. I've linked to the website of that and a white paper from a few years ago describing the platform. And then finally, the UN Big Data Working Group handbook on MPD for official statistics is well worth a read and has a lot of useful information. And that's me done, I think. Thank you.
Great, James. Thank you so much for this webinar. So before